The strangest stars in the universe lead us on a journey through some of the most profound stellar phenomena ever observed. From the baffling dimming of Tabby's star to the explosive outbursts of V838 Monocerotis, and from the massive nature of distant giants to the mysterious white dwarf companions like Sirius B, these celestial wonders push our understanding of stellar evolution and the physics that shapes our cosmos to their absolute limits. Join us as we unravel their mysteries and explore the deep astrophysical insights they offer. This is a long story, so let's settle in, but before we begin, don't forget to like and share. Some peculiar objects undergo random dimming events over short periods, making us question how stars are actually supposed to behave. These anomalies force us to rethink the laws governing stellar luminosity. They also raise intriguing questions about how material surrounding a star affects its brightness, how a star itself can change internally, and perhaps even hint at the presence of advanced technology from other worlds. This section explores the strange things that happen when light changes rapidly, examining one of the most famous cases and what these transient events mean for our grasp of how stars function. Since its discovery, the mysterious dimming of Tabby's star has bewildered scientists and become one of the most talked-after cases of strange optical behavior. Originally identified in Kepler data and quickly gaining attention, scientists noticed its luminosity would drop by as much as 20% in strange, seemingly random patterns. This brightness would plummet deeply and without warning, defying any known orbital mechanics. Unlike the regular dimming seen in binary systems or passing exoplanets, these events suggested something far more complex. Several theories have been proposed to explain this. One popular natural theory suggests the star might be surrounded by a swarm of comets or clouds of debris. In this scenario, uneven light drops could be caused by fragments or dust clouds periodically blocking the starlight. While this model is attractive for its simplicity, it struggles to explain the sheer scale and depth of the dimming, as well as the absence of a significant infrared signal that usually accompanies large amounts of orbiting dust. More speculative ideas have also been put forward, with some experts even imagining the dimming could be caused by alien megastructures, massive artificial constructs built by an advanced civilization to capture stellar energy. While highly discussed, this theory remains controversial and is generally treated as a last resort after all natural explanations have been exhausted. Newer research points toward intrinsic unpredictability as a possible cause, suggesting Tabby's star might have internal structures or dynamic processes that cause its brightness to fluctuate randomly. Despite extensive observations from ground-based telescopes and space missions, the cause remains unknown. Its light curve defies simple categorization, and no single model fully explains every observation. The fascination with this star lies in how its anomalous behavior forces scientists to look beyond current concepts and consider new ways that matter might behave in extreme stellar environments. Standard stellar models usually assume that on short time scales, a star's brightness remains largely stable, changing only slightly during known events like eclipses or rotation-driven star spots. However, these random dimming events break those expectations, forcing us to re-examine the complex processes governing luminosity. The challenge of these transient events is to explain phenomena that do not follow a regular pattern within the broader framework of stellar evolution. Traditional models built on the idea of stable nuclear fusion in a stellar core have difficulty accounting for deep, rapid, non-periodic drops in light. Since there is no discernible pattern, the dimming is likely not caused by simple geometric configurations. Instead, it may stem from more random or chaotic processes. Consequently, scientists are studying the long-term evolutionary changes of stars and their environments, considering shifting circumstellar material, sudden mass ejections, and interactions with complex magnetic fields. These transient optical events make us rethink how energy is produced and transported within a star. If a star's light changes rapidly without the usual signals of pulsation or rotation, it could mean other processes are at play, including changes in convective dynamics, instabilities in nuclear fusion, or even unknown energy transport mechanisms. These new ideas challenge the simplifications of our existing models and urge us to build more sophisticated numerical simulations to recreate the possibilities of stellar behavior under extreme conditions. Studying these events also helps us learn more about the death and rebirth of stars. Unexplained dimming could be a symptom or a precursor to major evolutionary shifts, such as the beginning of a supernova or the transition into a different stellar type. Astronomers use the timing, depth, and duration of these events to look for early warning signs of critical growth phases. These insights are vital for both theoretical models and our judgment of the future of our own cosmic neighborhood. These questions also impact how we observe the sky. To better capture these fleeting moments, traditional survey and monitoring programs may need to be adjusted, leading to the birth of new methods in time-domain astronomy. As instruments improve and data grows, we will likely find more anomalous stars, with each discovery testing our theories and helping us understand the diversity and evolution of the stars. A star originally catalogued as HD 100 and 1065, now often called Przybylski's star, is one of the most striking examples of its kind. It is famous for its extremely unusual chemical composition, with a spectrum dominated by an excess of rare earth elements and other heavy metals, while elements typically abundant in stellar atmospheres are significantly low. Conventional nucleosynthesis models suggest that elements produced inside a star should be distributed more uniformly, so this feature challenges those very models. The abnormal chemical variations suggest the star must be undergoing unique physical processes. One theory suggests that diffusion processes in its atmosphere are highly efficient, causing heavier elements to sink while lighter ones float, creating a layered, non-standard composition. Another possibility is that this strange abundance pattern is related to a past stellar merger or the replenishment of chemically distinct material from its surroundings. Whatever the cause, this outlier pushes scientists to rethink how stars generate and distribute elements. Models long considered reliable are now under pressure to incorporate these rare cases, which might mean introducing new physics or changing our understanding of magnetic diffusion and radiative support. As spectroscopy improves and models become more complex, such chemically peculiar stars remind us of the hidden complexity beneath a star's uniform glow. Another equally intriguing star is Babcock's star, known for its incredibly intense magnetic field, which is among the strongest ever measured. Such a powerful field has major implications for our understanding of stellar formation and evolution, especially regarding how magnetism affects energy transport and surface phenomena. In these stars, strong magnetic fields can suppress convection, altering how energy moves from the interior to the exterior and even affecting mass loss and the loss of angular momentum over time. Such a strong field can cause magnetic pressure to exceed thermal pressure in the atmosphere, leading to a highly ordered surface or even distinct magnetic patches. These patches leave unique signatures in the spectrum, allowing us to glimpse the star's internal machinery. The origin of such a field also remains a mystery. Is it a fossil field left over from the star's early years, or is it actively generated by a dynamo process in the convection zone? Studying these magnetic extremes has broader implications for all chemically peculiar stars, as strong magnetic fields are thought to inhibit chemical mixing, which may help explain why some stars show such odd element distributions. Furthermore, the intense magnetism of Babcock's star serves as a natural laboratory for testing theories of magnetohydrodynamics under harsh conditions, potentially offering new insights applicable to a wide range of astrophysical phenomena, from plasma behavior in the interstellar medium to the movement of accretion disks around compact objects. Together, these chemical and magnetic anomalies show that the universe is not a flat stage governed by simple, uniform laws, but a dynamic place where the extreme is often the norm. As observations increase and technology advances, our measurements and models will become more refined. These stars continue to demonstrate the diverse paths of stellar evolution and serve as critical testing grounds for how stars form, change over time, and seed the universe with new elements and magnetic phenomena. Gigantic outbursts and sudden changes overturn the intuition that stars are stable and predictable light sources. Instead, they reveal a hidden side of stellar evolution marked by instability and rapid transformation. These stunning events can manifest as powerful flares, sudden brightening, or even sharp drops, each providing a window into the complex processes within a star or its immediate environment. Such outbursts may signal major evolutionary milestones or be caused by mass ejections and interactions with surrounding material. In the early 2000s, V838 Monocerotis caused an astronomical sensation with an outburst that did not follow regular patterns. Unlike most novae or supernovae, this event saw the star's brightness surge to extreme levels before falling back very quickly, and its cause is still not fully determined. During the event, the star became many orders of magnitude brighter in just a few weeks before dimming again. What truly captured the public and scientific imagination was the resulting light echo. The light from the outburst was reflected by surrounding cosmic dust, creating expanding concentric rings of light. This effect was not only visually stunning but also allowed scientists to probe the star's environment and distance in a unique way. The cause of the V838 outburst is heavily debated, with one of the most popular explanations being a stellar merger. In this scenario, two stars collided violently, with the brightening coming from the energy released during the merger and the rapid dimming caused by the subsequent expansion and cooling of the outer envelope. The light echo acted like a cosmic shadow play, revealing the complex structure of the dust and providing clues to the merger process. Other theories suggest the event might have been triggered by a late helium shell flash, a brief but powerful increase in luminosity on an old star, but given the unusual spectral and photometric properties during the outburst, a merger seems more consistent. Detailed spectral studies revealed abnormal chemical signatures and temperature changes, supporting the idea of a rapid and chaotic restructuring of the star's outer layers. The light echo further allowed astronomers to map the three-dimensional structure of the circumstellar environment. This phenomenon is invaluable for measuring distance and understanding the distribution of matter around stars. While there is no absolute consensus, the stellar merger remains the best explanation for the anomalous behavior of V838 Monocerotis. In their early lives, some stars also undergo sudden, violent brightening that can last for decades, completely changing their appearance and revealing the mechanisms of rapid mass accretion. Young stars like Fu Orionis are typical of this eruptive behavior. These events are marked by a rapid rise in brightness caused by a runaway accretion instability in the disk surrounding the young star. These events overturn our common knowledge of constant, slow growth. Instead of a protostar brightening gradually, it surges periodically. The leading theory is that when a circumstellar disk becomes gravitationally or thermally unstable, matter suddenly rushes toward the star's surface. This not only boosts the star's brightness but also heats its outer layers, changing its spectral properties. Observations of these outbursts provide rich information about the physical conditions of young stellar environments. For example, during an outburst, the star's spectrum shows broadened absorption lines and shifts toward cooler temperatures over time, indicating that the expanded, heated disk material is contributing significantly to the overall radiation. This process effectively resets the star's evolutionary clock, allowing it to gain a massive amount of weight in a relatively short time. Such outbursts significantly affect the star's subsequent evolution, potentially determining its final mass and setting the stage for its life as a stable star. The Fu Orionis events also have a broader impact on the formation of planetary systems. Such violent and rapid accretion can strongly disturb the protoplanetary disk, which in turn influences how planets form and migrate. In some cases, the energy released during these outbursts can cause volatile compounds to sublime or redistribute dust and gas, thereby altering the structure of a nascent planetary system. Therefore, these one-time outbursts are not just curiosities of stellar physics but also critical hidden factors in understanding the co-evolution of young stars and their planets. Theoretically, the Fu Orionis events serve as a touchstone for testing physical models of disk instability and accretion. Astrophysicists are working hard to compare high-precision observations with complex numerical simulations to determine whether gravitational instability in the disk is dominant, or if magnetic fields and thermal processes play a larger role. Although the answers are not yet fully clear, our understanding of these complex processes is advancing rapidly with continuous observation and modeling. These studies not only illuminate the early stages of rapid stellar growth but also prompt us to re-examine stellar formation through a new lens where order and chaos coexist. In the early and late stages of stellar evolution, a small class of stars stands out for their unpredictable brightness and stability. A star's luminosity does not always change linearly over time. Instead, these stars fluctuate violently over days, months, or even years. Such irregularity often signals complex and poorly understood physical processes, ranging from pulsation instabilities and turbulent mass loss to complex interactions with circumstellar material. Astronomers believe that observing these anomalous celestial events will help them pinpoint the drivers behind massive changes and further understand the extreme conditions within stellar interiors. As one of the most famous red supergiants, Betelgeuse has long drawn attention for its abnormal variations in luminosity and the possibility of a future supernova explosion. As a massive star nearing the end of its life, the brightness changes presented by this celestial giant are both astrophysically fascinating and indicative of the violent processes within its massive convective envelope. Observations over the past decades show that the brightness of Betelgeuse is not constant and fluctuates significantly over time. The reasons for this variance are multifaceted. Unlike the Sun, which has small-scale granules, the surface of Betelgeuse features giant convective cells that can cover vast areas. These cells rise and sink, causing uneven heating and cooling of the photosphere, which triggers visible light fluctuations. Furthermore, upper layer pulsations occur as the star's outer regions regularly expand and contract, altering the luminosity output. These pulsations are driven by the complex coupling of internal pressure and gravity, creating light and dark cycles that are difficult to describe with a simple period. Additionally, dust obscuration plays a role. As a red supergiant, Betelgeuse is ejecting material at a high rate, which can cool and condense into dust. Changes in the amount and distribution of this dust block the star's light, leading to sudden dimming. A dramatic dimming event in recent years sparked widespread discussion, with some speculating it was about to go supernova, but further research showed the dimming was likely due to enhanced circumstellar dust rather than a direct sign of imminent core collapse. These overall characteristics strongly suggest that Betelgeuse is approaching the end of its evolution. As a red supergiant, most of its core nuclear fuel is exhausted, and it is undergoing rapid changes that will eventually end in a supernova. The light variations are seen as signals of this advanced evolutionary stage: increased chaos, intensified mass loss, and more complex internal dynamics. When it finally explodes, it may be visible during the day and provide scientists with an unprecedented research opportunity, reshaping our understanding of the star and profoundly enriching our knowledge of massive star death and galactic chemical enrichment. Another notable example is Eta Carinii, one of the most mysterious and deeply studied stars in the galaxy, known for its violent large-scale mass loss events and inherent instability. As a massive star in its late stages, it has undergone dramatic outbursts that changed its own structure and reshaped the surrounding interstellar medium. The Great Eruption in the mid-19th century briefly made it one of the brightest objects in the sky and ejected a massive amount of material, forming the famous bipolar homunculus nebula. This serves as a testament to the violent past of this stellar giant. A key feature of such stars is extreme mass loss. In massive stars like Eta Carinae, the radiation pressure pushing outward from nuclear fusion and the gravity pulling inward maintain a delicate balance. In its case, ultra-high luminosity drives powerful stellar winds that strip away the outer layers at speeds of thousands of kilometers per second. This mass loss not only affects brightness and temperature but also alters the internal structure, triggering subsequent instabilities and further eruptions. From a modeling perspective, the interplay of hydrodynamics, radiation pressure, and rapid rotation makes these stars a significant theoretical challenge. Reconstructing how radiation and fluids couple in a star losing mass at such an extreme rate requires high-resolution, multiphysics numerical simulations. Meanwhile, the fact that mass loss often alternates between outbursts and periods of calm makes predicting their evolution even more difficult. Observationally, Eta Carinae also exhibits significant short-term changes in luminosity and spectrum, further confirming its unstable nature as its outer layers rapidly restructure under the influence of pulsation and radiation. This complex behavior makes unified modeling difficult because the physical details behind different events can vary greatly. To complicate matters, it is located within a dense star cluster where binary interactions and external disturbances add new layers of instability. These interactions might trigger or modulate outbursts, but they also make it harder to identify the star's fundamental properties. Some stars are true titans, massive, energetic, and blindingly bright, pushing the boundaries of what we imagine is possible in the universe. These stars are the high-end products of stellar formation and the powerful engines driving galactic evolution. The nuclear fusion in their cores proceeds at such a rapid pace that they can light up entire nebulae, while their powerful radiation and stellar winds profoundly reshape the surrounding environment. When we study these giants, we find many members that are hard to categorize: red supergiants expanded to staggering scales, luminous blue variables with mysterious brightness changes hinting at internal instability, and even hypergiants that cross physical boundaries. The coupling between high mass, high energy output, and dynamic processes forces us to rewrite stellar evolution models, providing important clues about mass loss, supernova triggers, and cosmic chemical enrichment. R136A1 is one of the most stunning stars known, refreshing the limits of mass and luminosity and forcing us to rethink the upper limit of stellar formation. It is located within the dense and brilliant R136 star cluster in the Tarantula Nebula of the Large Magellanic Cloud. This is a famous starburst region, and its mass is thought to be over 250 times that of the Sun. It is one of the heaviest stars ever observed. Such massive weight causes its nuclear fusion to proceed at an unprecedented rate, making its luminosity more than 10 million times that of the Sun. This not only illuminates its surroundings but also has a profound impact on the ecology of the starburst region. The energy and strong winds it releases carve shapes in the interstellar medium, triggering the birth of new stars and influencing the evolution of nearby molecular clouds. In starburst regions like the Tarantula Nebula, conditions are extremely favorable for the rapid and efficient formation of massive stars. Extreme objects like R13601 provide key clues. How does stellar formation actually happen? In such violent environments, its extraordinary mass and luminosity stretch traditional evolution models to their breaking point. How does it form and remain stable within theoretically allowed time scales? Especially in environments with high pressure and strong turbulence, any viable formation model must simultaneously account for rapid accretion, significant mass loss, and the delicate balance between gravitational collapse and radiation feedback. This titan serves as an empirical yardstick for testing the limits of our models, providing a unique opportunity to refine theoretical frameworks. Research on this heavyweight giant has also driven simultaneous progress in observation and theory. High-resolution imaging and spectroscopy from modern instruments allow us to resolve its atmosphere, revealing abnormal spectral features and massive temperature gradients. From this, scientists deduce how its internal mechanics and energy transport maintain integrity under intense radiation pressure. Furthermore, the information it provides is vital for inferring the fate of the most massive stars. Will they end in spectacular supernovae or collapse directly into black holes? Stars like VY Canis Majoris represent the breathtaking boundary of stellar evolution as extremely rare red hypergiants. Its volume is so immense, reaching thousands of solar radii, that it challenges our existing knowledge of stellar structure and evolution. Its massive size is not just a visual wonder but a natural window into the death and rebirth processes of the most massive stars. Red hypergiants have extremely extended outer atmospheres and are significantly unstable. The immense gravity within drives extremely high energy transport outward, resulting in powerful stellar winds that strip away outer material in a relatively short time. These violent mass loss events determine the remaining mass available for subsequent nuclear fusion and set the stage for its explosive end. Structurally, the massive outer envelope exhibits large-scale, strong convective instability. Unlike the smaller, more compact Sun, macroscale turbulence exists in the envelopes of these stars, causing spatial and temporal non-uniform changes in temperature and brightness. The observed continuous luminosity variations may be a reflection of this constant restructuring and instability of the outer layers. These pulsations and convective motions both reveal internal structure and change the way mass is lost. Shock waves generated by turbulence push material away from the star. Such extreme volume makes it difficult for existing evolution models to fit directly. The combination of high luminosity and low surface gravity creates conditions dominated by radiation pressure, often forming complex and loose circumstellar environments filled with dust and gas, which both obscure observations and make physical measurements more difficult. Additionally, the observed massive mass loss suggests that the evolutionary paths of these stars may deviate significantly from classical theoretical predictions, implying the existence of alternative processes such as eruptive ejections or enhanced convective mixing. By studying these distant and extreme stars, we can improve massive star evolution models and understand how red hypergiants inject heavy elements synthesized in their cores into the interstellar medium, providing the raw materials for the next generation of stars and planets. Among the luminous blue variables, P Cygni is one of the most famous members in the galaxy and has been studied for centuries. It is known for its unique spectral profile, which indicates an extremely strong stellar wind. These features show that the star is losing mass at a staggering rate. The sudden increases in brightness and subsequent periods of relative calm seen in P Cygni are typical of these types of stars. This variation is caused by a delicate balance between gravity pulling inward and radiation pressure pushing outward, leading to periodic ejections of matter that change the star's outer envelope and affect its subsequent evolution. Eta Carinii is often seen as the prime example, where brightness can change significantly over timescales of years or even decades. Like P Cygni, stars in this class see a rise in brightness and a brief drop in temperature during an outburst, which is thought to be caused by the expansion and contraction of the outer layers during a heavy mass loss phase. This randomness and scale are at odds with the steady-state output assumptions of traditional stellar evolution models. These stars prove that the life cycle of the most massive stars is characterized by turmoil and dynamic change. Ag Carinii is another powerful example of a hypergiant, massive and extremely bright, while also exhibiting violent variable behavior. Its luminosity and spectral characteristics change significantly over time, showing a rapid restructuring of its outer layers. Like other similar stars, it undergoes alternating periods of outburst and quiescence. This cycle highlights the inherent instability of hypergiants and demonstrates the fragile balance between the core's powerful radiation pressure and gravity. Comparing Ag Carinii with other hypergiants reveals its larger amplitude and faster rhythm. Its light curve suggests that the processes driving these changes are highly dynamic, likely involving the coupling of multiple layers pulsation, convective activity, and eruptive mass E. The massive scale of HR 5171A presents several profound challenges to our understanding of stellar evolution. First and foremost, a star of such gargantuan size is expected to be inherently unstable. Its incredibly extended outer layers are subject to intense convective motions and pulsation instabilities, which lead to significant and periodic mass loss. In the case of HR 5171A, these instabilities manifest as irregular variations in brightness and a spectrum that shifts noticeably over time. Traditional evolutionary models, which work well for stars like our Sun or even medium-mass giants, often struggle to incorporate the chaotic processes found in hypergiants. In such extreme conditions, the interplay between outward radiation pressure and inward gravitational pull is exceptionally delicate. As HR 5171A sheds mass through powerful stellar winds, it is also losing the fuel needed for future nuclear fusion, altering its evolutionary trajectory in ways we do not yet fully comprehend. Furthermore, its immense luminosity exacerbates these issues. The vast release of energy creates such intense radiation pressure that the upper layers become even more unstable, leading to further mass loss. This creates a self-regulating feedback loop where mass loss changes the star's structure and evolution, making theoretical modeling incredibly difficult. To understand the dynamics of these massive stars, astrophysicists must employ highly complex multiphysics models that attempt to capture the fine details of convection, pulsation, and radiative transfer. Despite our modern computational power, many unknowns remain. The difficulty in modeling such extreme stars highlights that our grasp of stellar physics is incomplete and suggests that undiscovered factors may be influencing the stability and growth of hypergiants. Observational studies of HR 5171A provide a wealth of data to refine these models. By using high-resolution spectroscopy and interferometry, astronomers can probe the star's outer layers, revealing complex velocity fields and uneven mass ejection patterns. These findings show that a stellar atmosphere is not a smooth, uniform shell but a turbulent mixture of regions that together drive the star's changing light and spectral output. Deneb is another brilliant supergiant that has captured scientific interest due to its semi-regular variations in brightness, which provide clues about the instabilities of massive stars. Unlike stars with stable, periodic pulsations, Deneb's brightness fluctuates in an irregular and low-amplitude rhythm, suggesting complex internal dynamics and an unstable outer envelope. This peculiar behavior offers a unique window into supergiant physics and prompts us to rethink how energy is transported and dissipated in such massive objects. Long-term monitoring shows that its luminosity does not follow a strict cycle but rises and falls in a nearly random manner. These changes likely originate from large-scale pulsations within its dense atmosphere. In supergiants like Deneb, the balance between radiation pressure and gravity is fragile, and small disturbances can trigger large-scale structural changes. The semi-regular variations may result from the interaction of different pulsation modes. These waves traveling through the stellar layers cause the star to expand and contract periodically, which in turn changes its temperature and brightness. However, the nonlinear nature of these movements means other factors are involved, such as turbulent convection and localized mass ejections, which complicate the simple rhythm of pulsation. The irregularities seen in Deneb's light curve have deep implications for our understanding of supergiant instability. It shows that the processes governing these stars are highly dynamic and extremely sensitive to small changes, which can lead to large-scale consequences. This unpredictability challenges traditional models that rely on clearly defined periods. Instead, Deneb displays chaotic behavior caused by its massive yet thin outer envelope. This instability not only affects the star's luminosity but may also influence its long-term evolution, potentially altering its mass loss rate and ultimate fate. Spectroscopic studies further reveal its internal workings, showing that velocity fields within the atmosphere change over time, suggesting that different parts of the star move independently. This complex behavior likely arises from a combination of pulsation modes, convective processes, and rotation. By analyzing these spectral changes, scientists can better infer the structure and motion of Deneb's upper layers, providing invaluable information for improving supergiant models. Deneb's semi-periodic variations also affect how we understand stellar evolution in high luminosity regions. As one of the brightest and most massive stars, it occupies a critical position in the stellar life cycle. Its variability may be a symptom of deep processes occurring before more violent evolutionary events. Researchers are comparing Deneb with other variable supergiants to clarify the physical processes that lead massive stars from relatively stable burning phases toward their explosive ends. HD 140,283, commonly known as the Methuselah star, is one of the oldest known stars in the Milky Way and serves as a literal fossil of the early universe. Its ancient age and unique chemical composition provide key insights into the conditions of the primordial cosmos and the formation of the first generation of stars. The age of the Methuselah star has been a subject of much debate and reflection in the scientific community. Its estimated age is nearly 14 billion years, pushing right up against the estimated age of the universe itself. Determining such an ancient age requires precise measurements of stellar properties combined with advanced evolutionary models. The star's metal abundance is extremely low, meaning it contains almost no elements heavier than helium. This suggests it formed during a time when the universe was still chemically poor, before multiple generations of stars and supernovae had a chance to produce and distribute heavy elements. Its nearly pristine chemical fingerprint supports the idea that it formed from matter left over shortly after the Big Bang. Spectral analysis shows an atmosphere composed almost entirely of hydrogen and helium with only trace amounts of heavier elements. This scarcity of heavy metals challenges our understanding of how the universe became chemically enriched over time. Compared to stars that formed much later, the Methuselah star has been contaminated very little by subsequent generations of stars, preserving a chemical signature closest to the origin of the cosmos. By studying its spectral lines, astronomers can test models of nucleosynthesis and the evolution of the very first stars, exploring how these early populations influenced the later evolution of galaxies. The Methuselah star also serves as a laboratory for cosmological theory, providing a lower bound for the age of the universe. If this star is nearly 14 billion years old, the universe must be at least that old, which aligns with studies of the cosmic microwave background. This intersection of stellar astrophysics and cosmology reveals the tensions that can arise when a star's age approaches the age of the universe itself, pushing us to refine both our stellar models and our cosmological parameters. Its existence proves that stars began to form very early after the Big Bang, even when the universe was still in its infancy. This fact changes our traditional view of how quickly stars could form and prompts a re-examination of cooling mechanisms, like molecular hydrogen, in low-metal environments. In a sense, by studying this star, astronomers are peering into the life cycles of the first stars ever born. Although that first generation has not been seen directly, the Methuselah star helps us infer their properties and how the universe moved from darkness to light through generations of stellar nucleosynthesis. Its preserved chemical traces act like a time capsule, telling us about the temperature, density, and radiation environment of the early universe. Sanjolik -69202 holds a major place in astronomical history as the progenitor star of supernova 1987A. In terms of modern observation, this was the closest supernova seen in centuries. Traditional views held that the progenitors of such catastrophes should be red supergiants. However, This mother star in the Large Magellanic Cloud was a blue supergiant, overturning previous assumptions. The 1987 explosion provided scientists with an unprecedented window into the entire process, from core collapse to the ejection of enriched material into space. Before the explosion, the star itself was unusual. As a blue supergiant, it possessed high temperatures and intense radiation, with relatively low hydrogen content in its outer layers, contrasting sharply with the cooler, extended red supergiants typically associated with supernova progenitors. Its evolutionary path challenged existing models. How could a star evolve from the main sequence to a blue supergiant phase while still retaining enough mass to trigger a supernova? This case forced astrophysicists to re-examine the roles of mass loss, rotation, mixing, and binary interactions in the evolution of massive stars. Supernova 1987A provided a unique testbed for these updated models, with multi-wavelength observations helping scientists map the explosion mechanism and the formation of the complex remnant. In this case, the detection of neutrinos confirmed the neutrino burst that accompanies core collapse, just as theory predicted. Since then, the evolution of the remnant, including its expanding rings and asymmetric ejections, has helped researchers reconstruct the outer structure of the parent star. These findings both support key aspects of core collapse theory and show that we need more sophisticated models to cover the diverse paths of massive star evolution. Research into the star and its supernova has also deepened our understanding of galactic chemical enrichment. Heavy elements in the universe are primarily produced by supernovae, and the unique nucleosynthesis fingerprints seen in 1987A help us trace the origin of elements in later generations of stars. The anomalous features of the parent star also explain differences in the distribution of elements around the supernova, directly linking the final stages of stellar life to the chemical evolution of the host galaxy. V1309 Scorpii is a prime example of a luminous red nova, a type of transient astronomical event now commonly seen as evidence of stellar mergers. These events are thought to occur in close binary systems where the orbits of two stars gradually tighten until they merge, releasing a massive amount of energy. Unlike more violent supernovae, the luminosity of a red nova rises quickly and decays slowly, characterized by a distinct red color indicating that the ejected envelope is cooling. In the case of V1309 Scorpii, intensive monitoring showed a gradual increase in brightness followed by a rapid decline after the peak. Detailed analysis of the light curve and spectral evolution strongly suggests that this was not a typical nova or supernova but the result of two stars becoming one. Before the outburst, the binary system showed signs of orbital decay. Through tidal interactions and mass transfer, the two stars lost angular momentum, and their orbits grew closer. When they finally merged, the released energy caused a dramatic surge in brightness, while the cooling of the ejected material produced the signature red spectrum. As V1309 Scorpii reveals, these events provide a unique perspective on stellar contact and merger physics. It highlights how, in dense environments, the combined effects of gravity and angular momentum loss can drive extreme changes in binary stars. Although the energy released is less than that of a supernova, it is enough to outshine the combined luminosity of the two progenitor stars for a time. The result of a merger is a single, more massive star whose future evolutionary path is different from either of its predecessors. This process is crucial for understanding the evolution of binary populations and stellar statistics. By emphasizing the role of close binary contact, research into events like V1309 Scorpii challenges traditional views of single-star evolution. Given that a large number of stars in the galaxy are in binary or multiple systems, mergers may be more common than previously thought, and might help explain the formation of unusually massive or anomalous stars. These objects do not fit easily into traditional models, and mergers provide a natural explanation for some of the strange chemical abundances and structural anomalies we observe in the universe. The mixing of internal materials from two stars creates distinct characteristics that single-star evolution simply cannot produce. Furthermore, the study of V1309 Scorpii has driven significant progress in time domain astronomy. Scientists are now developing more advanced monitoring systems to capture these fleeting phenomena. Sequential observations of the pre-merger outburst and the post-merger remnant allow us to compare observable spectral and light curve data with theoretical models of energy dissipation, angular momentum loss, and mass ejection. This process imposes stricter constraints on the physics behind these spectacular events. Among the well-known white dwarfs, Sirius B stands as a classic case of a medium-mass star reaching its final stages. As the companion to the bright star Sirius A, it serves as a unique laboratory for studying how a star that was once hot, bright, and capable of maintaining nuclear fusion in its core transforms into a compact, degenerate object. The progenitor of Sirius B was once a brilliant star itself. Over millions or even billions of years, its core nuclear fuel was exhausted, and gravity finally triumphed over the outward pressure provided by fusion. The resulting stellar collapse left behind a white dwarf composed primarily of electron-degenerate matter. One of its most striking features is the extreme contrast between its small scale and massive weight. It possesses a mass comparable to the Sun but a volume no larger than the Earth. White dwarfs are characterized by this ultra-high density, where electron degeneracy pressure becomes the force resisting further gravitational collapse. The study of these objects has advanced our understanding of the fundamental physics of degenerate matter and how quantum mechanics behaves under extreme conditions. Specifically, white dwarfs like Sirius B provide direct observational evidence for the theory of degeneracy pressure halting collapse, confirming theoretical predictions made nearly a century ago. Sirius B also displays features that continue to intrigue scientists, such as a spectrum indicating a surface temperature that is relatively cool compared to its progenitor, a result of a cooling process that takes place over time. White dwarfs radiate away their remaining thermal energy over timescales of billions of years. Studying cooling curves like that of Sirius B provides a cosmic clock for dating stellar populations in our galaxy. Additionally, subtle variations in its spectrum reveal clues about the composition of its outer layers, helping us understand the processes of chemical diffusion and gravitational settling in white dwarf atmospheres. The evolutionary interaction between the two stars in the Sirius system is also noteworthy. The more massive Sirius A influences the orbital dynamics of the system and, to some extent, the evolution of its companion. For binary evolution models, the formation of a white dwarf in a binary system like Sirius is highly significant. Although Sirius B is now an isolated white dwarf, its final properties were likely shaped by previous interactions with its companion. Our broader understanding of binary star populations depends on this, especially for systems that may eventually lead to Type 1a supernovae. Systems like RR Lensis provide powerful examples of special binary evolution, where the interaction between two stars in close orbits produces strange and complex dynamic behaviors. As an eclipsing binary, this system provides precise timing information through its periodic eclipses, allowing scientists to monitor minute changes in the orbital period and infer structural changes in the system over time. One of the most striking features of RR Lensis is its unusual orbital dynamics. Unlike most eclipsing binaries with stable orbits, this system exhibits significant orbital variations, indicating a strong interaction between the two stars. First, their close proximity leads to powerful tidal forces that can deform the shapes of the stars and affect their rotation and orbital properties. This deformation not only impacts the timing and depth of the eclipses but also makes the overall dynamics more complex, potentially altering the orbital period. Observed shifts in the timing of the eclipses suggest the orbit is changing, likely driven by mass transfer or loss of angular momentum between the two stars. Mass transfer is one of the core mechanisms of close binary evolution. In systems like RR Lensis, one star may be at an advanced stage of evolution and losing mass to its companion. This redistribution of mass disturbs the gravitational balance, leading to the contraction or expansion of the orbit, which causes major dynamic changes. This affects not only the orbital period but also the spectral properties of the stars. The accreted material can change the surface composition and temperature of the receiving star. The complexity of mass transfer in these systems highlights the difficulty of theoretical modeling. Even minute changes in the mass exchange rate can have a profound impact on binary evolution. The interactions in RR Lensis are not limited to mass transfer. Gravity, magnetic activity, and even pulsation waves work together to further complicate the system's behavior. Sometimes these interactions can lead to changes in orbital eccentricity or even the temporary formation of an accretion disk around one of the stars. High-resolution spectroscopic research has found subtle variations in the spectral lines of RR Lensis, indicating that the stellar atmospheres are constantly changing under the influence of binary interaction and internal pulsations. The abnormal orbital dynamics of such systems have broader implications for our understanding of binary evolution. Many stars in the galaxy exist in binary or multiple systems, and the interactions observed in cases like this can dramatically alter the evolutionary paths of the participating stars. Mass transfer in close binaries is considered essential for the formation of certain outlier objects, such as blue stragglers, the progenitors of Type 1a supernovae, and even certain neutron stars and black holes. That concludes our knowledge sharing for today. I wish you all a wonderful dream and a beautiful day ahead. See you next time.